for 31 quiz 8 should look like this. An alternating EMF source with a variable frequency is connected in series without a capacitor. So this is basically an RL circuit. All right, so let's make a drawing. All right, let's draw as we read. An alternating EMF source with a variable frequency. Here's an EMF source with a variable frequency, also known as a generator. So a generator produces is a source of alternating power, alternating current, alternating voltage. When you plug in your device to the wall outlet, that's actually alternating current that is generated by DTE energy or consumer's power. It's connected in series with an 80.6 ohm resistor. So there's the resistor, R for resistor, and a 42.5 millihenry inductor. There's my solenoid. Remember, inductors are basically solenoids. And remember, a solenoid is basically a slinky, a bunch of coiled wire. RLE. So this is not an RLC circuit, it's an RL circuit. Okay, the EMF has an amplitude of 6.05 volts. So that means this power supply is generating an alternating current. And what that's referring to right here is this alternating current has a peak value right there given by that gray line. And this peak value, it hits a peak value of 6.05. E equals 6.05 volts. Okay, so that's what that's referring to. Consider a phasor diagram for the resistor and the inductor. Okay, well, let's set up our phasor diagrams. Here is okay, let's do that. So I'll just sort of do a generic setup of a phasor diagram for the voltage drop across the resistor and the inductor. Here's my resistor at some arbitrary time. So this is not at time equals 0. This is at some arbitrary time like that. So how much time ticked off the clock? This much time. This is omega D equals, this is theta equals omega D times T. So this is a particular time. This is a particular time. At some particular time, we're looking at what's happening. And so this is just some arbitrary time where if we wanted to look at 1.5 seconds, then T would equal 1.5 seconds. This omega D, this is the angular frequency of my source, angular frequency of source. So remember, most electricity is generated by spinning magnets, angular frequency of source. Okay. So this would be my voltage drop across the resistor. These phasor diagrams are just very convenient ways to sort of represent what's happening. A phasor diagram basically says what's going on with the driving EMF, the resistor, the inductor, the capacitor, all on one graph. And there's quite the learning curve, I think. But once you learn it, it's very helpful. All right, so this is my voltage drop across the resistor. And I remember from Eli the Iceman, that Eli means the following. Eli means inductor voltage. Voltage leads current for an inductor. That's what Eli means. Voltage leads current for an inductor because voltage, this is voltage, and voltage is referring to the E in Eli. This is current right here. Current is referring to the I in Eli. And we're referring to the voltage and current relationship of an inductor, which is this variable right here. Inductor here is referring to that L. So Eli the Iceman is the mnemonic that reminds you that for an inductor, voltage leads current. So let's draw that. So here is my, that's too thick. That's not a line. There. Okay. So this is the voltage drop across my inductor, VL. All right. There's always that 90-degree relationship. And let me just draw your attention again to, I think, a very helpful summary page right here. This isn't all of chapter 31, but this, I would say this is kind of like the a distillation of chapter 31. So just make sure this is a good at a glance. This is alternating current. This is a summary of alternating current. Sort of the one thing that's missing from this page is power and RMS, which we'll get to today. Okay, so let's go ahead and back to the problem here, quiz 8. All right. Oh, and then if you notice in the summary diagram, it tells you that, well, in an RLC circuit, the inductor voltage leads the current by 90 degrees. So everything's in here, pretty much everything. But your pushback would be, well, Chris, you're showing the voltage across the inductor leading the voltage across the resistor by 90 degrees. And Eli the Iceman says, no, Eli the Iceman is saying that inductor voltage leads current. So I need to do this. I'm going to do one little current, one more little. All right, so there. I'm going to draw this. This red vector is I. This I, and I is the current going through the circuit, and I is like the great unifier. I is current, and the great thing about current here is current is the same everywhere. There's no such things as phase differences. Current is same everywhere. So it's the great unifier. It's like the system clock. Current is the same everywhere. Okay, so and why are these in phase? Why am I drawing this red vector, which is the circuit current? Why is it perfectly lined up with this green vector, which is the voltage drop across the resistor? And that's because a resistor, the resistor is basically a current is in phase with the voltage drop with a resistor. Remember what an inductor does. An inductor has some electromagnetic properties. An inductor behaves like a has some inertia, it chokes the current. It's, in fact, a lot of times inductors are referred to as chokes. And remember, a capacitor has a certain profile too, but a resistor is just sort of a dumb physical device. There's nothing exotic from an electromagnetic point of view about a resistor. The current going through the resistor is just completely synced with the voltage drop across the resistor. That is not true with an inductor. That is not true with a capacitor. So that's why these two vectors are lined up, the green vector and the red vector. And that's why you can see there's Eli. There's the Eli part of Eli the Iceman. Eli the Iceman is right here. This blue vector is leading the current by 90 degrees. So that's the phasor diagram. So we're done with consider a phasor diagram for phasor VR. Consider a phasor diagram that includes the resistor and the inductor. Okay, I did that. At what driving frequency do the two phasors have the same length? So here is let's do a copy and paste. Here's my phasor for the inductor. Ready? So I'm just going to Control C and Control V right there. Okay, that's my inductor phasor, VL. And now the question, and then here's my resistor phasor. Let me copy and paste that. Copy and paste. Okay, this is VR. So it's just phasor diagram, basics of phasor diagram, VR. And now the question is, what does your driving frequency need to be so that these two vectors have the same length? In other words, I'm going to set my EMF frequency so that that green vector and that blue vector have the same length. So let me just do green vector. So I'm just eyeballing it. I want to make them the same length. That's my design goal here. All right, so let's say those are the same length, and I'm not going to forget that these are at 90 degrees with respect to each other because of Eli. All right, so here's my problem. Part A is, number one, what is A? What driving frequency did these two phasors have the same length? So I'll say at F equals $ VL equals VR. That's the task. That's your design goal. You have to set the frequency of that driving EMF so that those two phasors have the same length. All right, so number two, let's keep going with that. What's VL? Well, here's Ohm's law. Here's what I'll call it. AC Ohm's law. AC Ohm's law for an inductor. Well, in general, you know that V equals IR. That's regular old Ohm's law. AC Ohm's law for an inductor is still the same. It's V equals IR, but we don't say V. Let's personalize this for AC. It's, well, for an inductor, it's V across the inductor equals the current I times the resistance. And for an inductor, we don't use R for resistance. We use XL for reactance. So remember what XL is. XL is basically the inductor's resistance, or sort of the pushback. XL is called inductive reactance, and it's basically referring to the pushback or the resistance that is represented by the inductor. So VL equals, so that's Ohm's law. This is AC Ohm's law. AC Ohm's law.
Excuse me, Professor Wood.
Yep.
There's a text on group me. Matt Jackson still needs to be let in the session.
Okay, let me go see. Let's see. Okay. All right, so that's also, Ohm's law.
While you're on pause, I actually can't open the quiz like at all.
Anyone else having that issue?
It's like not even like opening like the screen for me to like open the assignment or any assignment on Wiley Plus.
Does anyone else have that issue, or is that just Mo? So Mo, apparently everyone else is able to get into this exam. So I guess my
actually
standard...
It just loaded up now.
Okay.
I've been trying since the start of this quiz. My bad.
Okay. I was just going to say, like, log out, refresh, just standard restart attempt.
Oh, I tried that like 4 times. Yeah.
But it's working now?
Yeah, it just started working now.
Okay. Must be a sunspot or something.
All right.
But you're in shape. That's good. Okay. So here's regular old Ohm's law that we know and love. Here's Ohm's law personalized for AC in general, and even more specifically for inductors. And then, and here's Ohm's law for a resistor. There is no such thing as Ohm's law for a voltage drop across a resistor, because again, a resistor doesn't have any weird electromagnetic phenomena going on. So the voltage drop across the resistor is just going to equal the current going through a resistor times the resistance. So these are my two Ohm's laws expressions. This is Ohm's law for a regular old resistor. This is Ohm's law for the voltage drop across an inductor. Okay, so now and I'm going to repeat one more time. The great unifier here is the fact that the current is the same everywhere. Voltage values vary. Voltage values are, the EMF, the voltage drop across the resistor, the voltage drop across an inductor, the voltage drop across a capacitor, these are all out of sync. They are not synchronized, but current is the same at all times through every device element. All right, so that's very helpful. We use that a lot. That fact is used a lot. Number 3. All right, so the question, at what driving frequency do these two phasors have the same length? So I'm keeping my eyeball on the green vector and the blue vector. Okay. So if VL equals VR, that means that I times XL equals I times R. Low-hanging fruit, you can see how the current cancels. So now it boils down to this. Basically, I have XL equals R, and somewhere in here needs to live my dollar sign. My dollar sign is the driving frequency of my source. So I'm just going to keep stringing this along willy-nilly. Omega D times L equals R. Okay, so this is, I'm still not seeing my dollar sign. Well, I kind of am seeing my dollar sign, but this is the expression. XL equals omega D times L. And I'll just refer you to the handy dandy summary sheet, summary page. It's on the summary page, but you should go through don't let yourself fall into the trap of just being an equation operator. If you just look up equations on your green sheet to your summary page and you plug them in, that's not going to be what you think it is in terms of your proficiency and mastery. So having said that, number 4. Okay, so omega D. So, well, here's omega D. Omega D is 2 pi F. So there's my dollar sign. Omega D times L equals R. There's my dollar sign right here. And we know from birth of a radian for the umpteenth time has shown us that omega equals 2 pi F. So if I wanted to personalize that here, I would say, well, I'm looking for specifically the driving angular frequency. So the driving angular frequency is 2 pi times just the regular old linear frequency, driving frequency. Omega subscript D is driving angular frequency. F subscript D is just driving frequency without the angular. All right, so there's our dollar sign right here. Number 5, solve for FD. Solve, and then let's put that in our calculator. Remember, because just in case we need it. Solve for FD. So I get FD equals some number. All right, so R, we do know the resistor value. 0.0425. Okay. All right, I have a value. I'm going to put that in calculator memory location A. Store alpha A. So if you drive this particular circuit with that frequency, as if by magic, that green vector and the blue vector have the same length, which means the voltage drop across the resistor is the same as the voltage drop across the inductor. And that's a good thing to know how to do, depending on the application. All right, so that's A. B says, what's the phase angle? So now we have to talk about the meaning of phase angle. All right, so I'm going to go back to the ultra important phase diagram on that left side here. So I'm going to just do a copy and paste here. Phase angle, let's take a look at the phase angle. So there's my blue vector. Let me zoom in. Okay, so here's my phase diagram. This is VR. This is my voltage drop across my inductor. That's the voltage drop across my inductor. Okay, so I'm just lining things up head to tail. So when I say head to tail, I'm saying here's standard vector operations. It's tail to head, and then it's this tail to head. And you keep playing that tail to head. You keep doing that tail to head stacking until there are no more vectors to deal with. In this case, there were only two vectors, the green vector and the blue vector. So this is my EMF voltage at a particular time. What's a good color? Orange. Right here. All right, so first tail to last head. Okay, and this is EMF. At any point in time, this orange vector is telling me what the voltage is coming from my supply, coming from my source. So this orange vector is the voltage that I'm getting from my source, which is right here, the source here. And the phase angle is defined as this. Let me clear the deck a little bit here. All of that is in the past, we know. All right, phase angle is always defined as this angle right here between the source voltage and the circuit current, phi. That's fine. I'm going to actually write that out just because it's important. And all of this stuff is makes your head spin at first. I understand that. But after a while, it's familiar. All right, so phi is the phase angle, and it's the angle, it's the phase, it's the angle between the EMF voltage, which again is brought to you by DTE or Consumers Power, whatever, and current. Okay, that is the phase angle. So you got a written description of it right here, and you have a visual staring right at you. And in this case, what is that angle? And it's kind of easy because we engineered this situation so that these two vectors are equal. So remember what the question was. What's the driving frequency? What's the driving frequency so that this voltage drop across the resistor, it has the same value as the voltage drop across the inductor? Those are equal. So if these are equal, let me draw that so it looks a little bit more equal. If we engineered it so that those two voltage drops are equal, then you can see that I have an isosceles triangle. So phi equals 45 because these two are always, this is always a right angle. That's always a right angle. And in this case, this voltage drop is the same as this voltage drop. So this is going to be simply 45 degrees. Okay, so we're done with A. We're done with B. Part C says, what's the angular speed at which the phasors rotate? So we've already figured that out, but it just gives me a chance to hype this right here. So, ask yourself, make sure you're clear, you guys, make sure you are completely aware of what is this right here? What is theta equals omega t over t? And this goes back to your other physics class where the definition of omega is theta over time. Just like in the good old days, the definition of velocity was distance over time. So we don't say velocity equals distance over time. We say angular velocity equals angular distance divided by time. So that's where this omega equals, theta equals omega dt comes from. So we're just saying at a particular time, at an arbitrary time, if we said what's going on at time equals 0, then this black vector would just be completely in that direction. But we're not. We're looking at what's going on at just some arbitrary point in time. Part C says, well, the frequency that produces this result, the voltage drop across the inductor being the same as the voltage drop across the resistor. What's the angular speed? And we have that right from number 4. So let me zoom out. All right, number 4. So I'll do number 6. Number 6, part C is saying omega d, angular speed, and omega d equals the $sign. And then as mentioned from number 4, look at number 4. From number 4, don't even have, we have omega equals 2 pi f, maybe subscript d, because again, we're talking about the driving frequency that is created by the source. So equals 2 times pi times calculator memory location A. So let's do that. 2 times pi times A. Okay. 1896 and some change. 1896 and some change. And it wouldn't be hertz, it would be radians per second. Done with C. D. What's the current amplitude? All right, so let's finish this. Number 7. I subscript M stands for current amplitude. Current amplitude. Current amplitude means the following. The max current. It refers to the maximum current. Current is behaving like this. So current is doing the whole sine wave thing. So I max is referring to this peak value right here. What is that value? This maximum value is referred to as current amplitude. Okay, so number 8. Number 8, let's use Ohm's law. Ohm's law, what is the current amplitude? Here's AC Ohm's law. AC Ohm's law says the following. It says, well, it doesn't say V equals IR. V equals IR becomes for just the current amplitude. I don't say V, I say E for EMF. I still say I, and I don't say R, I say Z. So this is AC Ohm's law right here. Okay, so let's run with that. Number 9, number 10. Let's isolate I. In fact, I should write this down. This is E, and I should write that. That should be an M. There should be an M there, and there should be an M there, and there should be an M here. So that would be a mistake not to include that. I need to include M for max value or amplitude values. Whenever I say amplitude value, it means max value. That's the vocabulary, I guess, that we use. All right, so if that's true, that current amplitude, the maximum possible current is my EMF over my impedance. My EMF is given as 6.05 volts, 6.05 volts, all over impedance. And we remember impedance is the overall aggregate resistance to current flow. And it's sitting right here, basically. It was based on Pythagorean theorem. It's R squared plus XL minus XC squared. I'm going to move some things out of the way. There is no capacitor here, so this suddenly got a lot easier. Number 11. So the maximum current, the maximum value reached by my current going through the circuit is 6.05 volts all over the square root of my resistor squared. For me, the resistor value is 80.6 ohms squared. There is no capacitor, so let's take care of some low-hanging fruit. No capacitor means no capacitive reactance. And then here's another aha moment. Aha. Another more low-hanging fruit. Aha. XL equals R. Because remember what the whole gist of this problem was. What driving current do you need to use so that this is true? And we did that. We figured out the driving current so that the inductive reactance is the same as the resistance. So then I'm just going to do this. Plus 80.6 omega squared. And that should be the answer. Turned out to be easier than I thought. Okay. All right. .05307. So I know my current hits a momentary max value periodically of that 53.07 milliamps. So that's the answer to part D. So this was an RLC circuit without the C, so it's really an RL circuit. It was a driven, this whole thing here was a driven RL circuit. I remember last time we had a driven RC circuit. This is a driven RL circuit. Okay. Give me a moment to set up our next quiz. Okay. Actually, let's do this. We're going to change gears. We need to Falstad this because we have time, and we need to do Falstad. All right, so go into Falstad. Everyone off to Falstad circuit. And this will count as another quiz. So this Falstad app is technically a quiz in and of itself. So this is what I'm saying. Go ahead and get into Falstad full screen version. And again, you guys, don't be shy to unmute your mic and speak up if you have questions or requests, or if you want me to maybe hurry up or slow down. Otherwise, I'm assuming I'm moving at the perfect pace and explaining everything absolutely perfectly. All right, so we're in Falstad, the full screen version of Falstad. We're going to model this circuit. Step number one, circuits, blank circuit. Okay, let's create this RL circuit. And then the other thing I like to do, maybe you'd like to do this too, under options, select show cursor crosshairs. That makes lining things up easier, I think. So right click anywhere on your workbench here, and then let's do inputs and sources, add AC source to terminal. I'm going to do this twice. I'll go through it quickly once and then again. There's my EMF. Ta-da. There it is. Okay. Let's right click, add a resistor. Done. Right click, add an inductor. An inductor is under passive components. Add an inductor. Done. Nice and lined up. Right click one more time, add wire, complete your circuit. So there's my circuit. This is my driven RL circuit. Let's all use my numbers for this, just so I can grade things efficiently. All right, so we're going to use my numbers. Let me make them easy to read. All right, my resistance is 80.6. So double click on your resistor value. Double click on your resistor value, 80.6, 80.6. My inductor value is 42.5 millihenry. So you know what you can do? Double click on your inductor, double click, and just type in 42.5 M. M for millihenry. It's that easy. You don't have to you don't have to do the conversion. 42.5 millihenry. That looks good. My AC source is cranking out a peak amplitude of 6.05 volts. So change the max voltage to 6.05 volts. So, and you can see, I mean, you actually have a good visual. You're looking at a pretty efficient circuit. You can see how, let's just say for the sake of conversation, I change this to 500 ohms. It's a lot more sluggish. You can see the current there. I still have oscillations and things are happening, but it's just not nearly as great as it was when I had this. And it's going to get even better because now we have to drive this power source at precisely 301 point something. So let me take a screenshot of that. Well, here. How best to do this? I have it in my calculator, I think. I do. All right, so here's the number. Here's the number. Here's the driving frequency that will create equivalent voltage drops across the inductor and resistor. So double click on your source. There's my 6.05 volts. And now for frequency, let's all use 301.832.6685. And that's the frequency with my numbers. With these numbers here, if I use this frequency, at any moment in time, my voltage drop across the inductor will match the voltage drop across the resistor. So say apply. There it is. So this isn't resonating. Well, there's no such thing as resonance in just an RL circuit, but this is producing equal voltages. So I'm going to do the following. I'm going to just start all over. Circuits, blank, and then I'm going to right click, inputs and sources, add AC voltage source to terminal. There you go. Right click again, add a resistor. Yes. Right click again, passive components, add an inductor. Finally, right click one more time, add a wire, and close the circuit. Change your resistor value from whatever its default value is to 80.6. Double click on the resistor and set it to 80.6 ohms. Okay. Change your inductor value to its default value to 42.5 millihenry. And I can do that just by double clicking on the inductor and saying, hey, inductance is 42.5 M for millihenry. Double click on that voltage source and set the max voltage to 6.05. That was my number. 6.05 is that peak voltage produced by that source. And as long as you're here, set the frequency to the value that we figured out using math and physics that will produce the same voltage drop across the inductor and resistor, which was 301.832 6685. Ready, set, go. Okay. So there it is. Now let's start graphing stuff, because if we played our cards right at any moment in time, the voltage drop across the resistor is going to be the same as the voltage drop across the inductor. So let's investigate that. Put your mouse on top of the resistor and right click and select view in new scope. View in new scope. There it is. And then let's do this. Take your scope and let's make it big. Enlarge your scope so it's really easy to read. Okay, so now we're looking at the resistor in the scope. So the scope is the graph. Right click anywhere on the scrolling graph. Right click, properties, and then let's do a few things. Let's not look at the current. So deselect current there. Let's change the horizontal scale from 10 milliseconds per division to that looks good, to 200 microseconds per division. So then say, okay, and then let me repeat that again, as if I didn't do this at all. I'm saying if you got your things going here, if you got your circuit going, hover your mouse over the resistor, right click and select view in new scope. And your view in new scope should occupy just a small strip along the bottom, but grab it, find the top control and enlarge it so it's really easy to read. And once you do that, right click anywhere on this strip graph and right click anywhere on the graph and choose properties. And we're doing two things. We're changing this from 10 milliseconds per division to 200 microseconds per division. See how it's easier to see now? And then let's turn off voltage and just keep current. I'm sorry, turn off current and keep voltage. So we're just looking at the voltage drop across that resistor and then say, okay. Finally, select or hover your mouse over your inductor. With your mouse cursor on top of your inductor, right click and choose add to existing scope. Click. There it is. Add to existing scope. All right. So let's do this. I'm going to stop. Okay. I'm going to stop the scroll. So I stop the simulation. Hover your mouse over the inductor. And when you hover your mouse over your inductor, you can see the graph highlights for it. So when I move my cursor over the inductor, you can see that sine wave there highlights. When I hover my mouse over the resistor, it's that sine wave. So according to my graph, this red trace is being used for my inductor. And again, I'm just going to double check this. If I hover my mouse over the resistor, this green trace, wait a minute. Inductor voltage. Yeah. The green trace is for the resistor. So I just wanted to confirm that. So let me just back up since I got turned around for a minute. Put your mouse on top of the inductor and so put your mouse on and off. So on, and you can see the red, for me, it's red. The red trace represents the voltage drop across the inductor. And let's just double check. Hover your mouse on and off the resistor. And you can see for the resistor, it's the green trace represents the voltage drop across the resistor. All right. So this is showing what we thought it should show. Just let's look at any particular point in time. Well, I think that's good for now. Let's do one more thing, and then you're going to submit this. You're going to submit a link to a group chat. Okay. So here goes. And you can see the voltage values are the same. So this is what we were hoping for. My peak voltage across my inductor is 4.278, and my peak voltage across my resistor is also 4.278. But let's do this. If we look at this problem here, let's verify the current amplitude. We did all the math and physics to cough up what the current amplitude, the current amplitude should be if we design the circuit like this. So let's just verify that. Back to Fallstad. All right. Right click anywhere on the graph area. Right click anywhere in the graph area. Right click properties. And then let's do show current. Show current. And then the other thing we have to check is show peak value. So in fact, I'm just going to do this. So the only two boxes I have activated for this graph are show current, that's checked, and show peak value, that's also checked. All right, so everything else is unchecked. I still have that same 200 microseconds per division. And let's run it. 3, 2, 1, run. Okay, there it is. So you're looking at the current bouncing through the circuit, and this current is the same everywhere. It's the same through the inductor, same through the resistor. And if you notice top left, it's Fallstad is saying your maximum current is 53.077 milliamps, which I believe is what math and physics says, 53.077. So we have confirmation. So now what you need to do is ask questions if you're not clear about anything. But I'm assuming we're all at the same point in this. Let's do the following. Click on File, and then choose Export as Link. And then click on the button that says Create Short URL. So there's my short URL. So let me repeat that, because then you're going to copy and paste this into the chat box. And then that's how I will grade things. All right, so I'm going to repeat that. File, export as link. I don't want you to paste. I don't want to deal with that gigantic URL. So just create a short URL by choosing Create Short URL. And then copy to the clipboard. And then go ahead and in the chat box, paste. Oh, and Chris Goulet already did it. Chris is done. Well done, Chris. Let me just click on yours to see how you're looking there. Top drawer. That is some top drawer stuff. That's some top drawer stuff from Chris, Luke. Okay. Very nice. All right, good. And I can check. I'm just going to let this scroll in, and I'll just click on it, and I'll just do some verification. And that's how you're going to earn quiz credit, as if by magic. So good. Everyone's good to go. So this is to me, I like this. I don't have to set things up in Blackboard. You don't have to log into Blackboard. You just send me a little URL, a little short and link in. Life is good. So everyone has now submitted their link. Let me go on, and I'm just going to let that accumulate in the chat box area. All right, so now 8:52. Let's start. Let me take a look at the next problem to see how daunting it is. It's pretty daunting. Okay, well, then let's just at least get a start on it. I'm going to open up quiz 9, and we'll take a break halfway through it. All right, so, okay. Let me go into Wiley Plus. Chapter 31, quiz 9. Okay, check it out and don't remain silent if you're not seeing what I think you're seeing. Chapter 31, quiz 9 should be problem 57. It should look like this. If it doesn't, please let me know. And this will take a bit of time. So maybe we'll take a break shortly, depending. All right, so let's go. Here we go. Chapter 31, quiz 9. We'll do some more Falstad on this because all of these lend themselves to Falstad, which is just a great activity. Now we have an RLC circuit. Now we have RL and C as an RLC circuit. This is at the heart of so many practical applications. My favorite is basically it's the grid. This is our power grid. So even if we completely eliminate fossil fuels, we still have our grid, which will behave according to these basic principles to a large extent. So that's what keeps me interested. All right, so let's go ahead and read in an RLC circuit such as that of the figure. You have RL, a driving frequency. Now we have to find capacitance. All right, so this is the first time we talk about this is the first time we talk about something known as RMS, root mean squared. And let me do something I don't typically do, but I'm going to do it now because there happens to be a unusually good, by my standards, yet poor quality, good but poor video quality video. Let's go through the following. Let me cue this up. We're going to watch, I think, maybe 2 minutes of this entire video. And again, it's not great production quality, but who cares? It's the idea that matters. And this is just a great way to talk about how we typically deal with alternating current in terms of average values. We typically use root mean squared values. So let me just adjust some things here. All right, so that's that. All right, so not a big fan of showing video clips over Zoom, but I'll make an exception here, and hopefully you'll see why. Here goes.
This video is about AC and DC. And on my oscilloscope, the red line represents the DC, and the blue line represents the AC, which is currently off.
Screen is black for me.
And RMS. That would be a good other.
Yeah, you're right. So again, no need. Thanks for speaking up.
This video is about AC and DC. And on my oscilloscope, the red line represents the DC, and the blue line represents the AC, which is currently off. I could call it peak and RMS. That would be a good other title. I have here a battery pack, and I'm using it to make this bulb light up with DC. I set it to be almost exactly 3 volts. We can see that on the oscilloscope screen, 3 volts. Now, I'm going to turn up the AC, which is set to quite a high frequency, so you can't really see it flashing, and hopefully you'll see it increasing on the oscilloscope screen, and you'll see the bulb just beginning to glow. Now my question is, what value of AC do I need to make the bulbs glow at the same brightness? Well, at the moment they're clearly not the same brightness. This is much dimmer, but the AC is a lot smaller value. Let's increase it until the AC is touching the red line. So now the AC and the DC are the same maximum value. The peak level of the AC is the same as the DC, 3 volts. Are the bulbs the same brightness? No, they're not the same brightness. And therefore, we obviously need to have a little bit more AC. And if we keep going, up to about, and you have to judge this by eye, it's quite difficult to do. The camera plays tricks. But to me now, in the lab, they look about the same brightness. And you can see that to achieve that, the ACs had to go quite a lot higher than the DC. Let's read what value it is. And it's about 4.19, 4.2 volts. So, get rid of the oscilloscope and label this one as 4.2 volts. And then let's see if we can add any of our theory into place. So we should know that the AC value is represented by the peak voltage, which in this case is 4.2 volts, and we have an equivalent DC voltage, which in this case is 3 volts, and those create an equivalent lighting effect. Therefore, 4.2 volts AC is equivalent to 3 volts DC. This value here is what we call the RMS value. It stands for root mean square. It's the average. And the equation that links them together is quite straightforward. We should be able to find that the peak voltage is equal to the RMS voltage times by the square root of 2, as long as we're using a sine wave. If you use a square wave, it's different. So let's try out those values and see if they actually work. So what we'll do is we'll take our calculator and we'll do our RMS voltage, which is 3. We'll multiply it by the square root of 2. You've got to love this calculator. And it tells me it's equal to 3 root 2. Thanks a lot for that. But if we convert it, it actually shows it's 4.2 volts.
Okay. So I like that video just because it's really straightforward and you have 2 light bulbs just sitting there in front of you. And that's root mean squared. RMS stands for root mean squared. If you look at your lecture notes right here, there's actually a more mathematical background that I provide. I provide a deeper mathematical background, but I wanted to show that video because it's always good to have sort of like a gut feel or, you know, an audio visual understanding of what the math is saying. And it's basically just taking the average of a sine wave. How do you take the average of a sine wave? That's what root mean squared is talking about. So let's do this problem. Let's get a start on chapter 31, quiz 9, because we need to deal with averages. And whenever you deal with averages in the world of AC, you are talking about RMS. And basically, whenever we talk AC, anything, any number we talk in whatever context, just like in the classroom or on the job or whatever the situation is, when you're talking numbers and you're speaking, relative to alternating current. The numbers you're blurting out are the RMS values. So that's sort of the standard approach. We have an RLC circuit. For what values of the capacitance would the average rate at which energy dissipated in the resistance is a maximum? So let's talk about part A. Part A is we're finding this out. What is the value of the capacitance so that the power dissipated in the resistor is a max value. I'll write it like that. Okay. That's what part A is saying. Let me just read it. Go ahead and figure out the value of your capacitor so that your resistor is burning up as much power as it can. So this is a job for P equals I squared R. This formula right here, believe it or not, was introduced all the way back in chapter 27. P equals I squared R. And power itself was introduced back in chapter 8 or whatever chapter you used in your class. But this is known as, this is power dissipated by the resistor as heat. Just think of your toaster or your oven or your cooktop surface. You send current through a material that is intentionally made to be highly resistive. And that's because if it's highly resistive, it converts that electrical energy to heat energy. Power dissipated by resistor as heat. Okay, that's what I squared. In fact, a lot of times you hear people refer to as I squared R heating. In fact, my downstairs furnace isn't working. I have to fix my downstairs furnace. True story, actually. I have to do that today. And basically, if I'm referring to the heating of a furnace or a stove or an oven or anything, a lot of people just call that I squared R heating. A lot of people meaning like engineers or technical people. All right, so part A says, what do you have to do to that capacitor so you get a maximum heat dissipation? So number 3, I'll keep my narrative going here. Max heat is produced by the resistor when I get I equals I max. I need to find out the maximum. I need to figure out how to get the maximum current flowing through that circuit. Because if I can get the maximum current flowing through this circuit, I'm going to get the maximum amount of heat dissipated by the resistor. So this is my first aha moment. Aha. This happens at resonance. Remember what resonance is. This happens at resonance. Resonance is the perfect balance between the inductive reactance and the capacitive reactance. This happens at resonance. Okay. Resonance means whatever is going on with the resistor and with the inductor, they're basically working efficiently with each other. Instead of being kind of out of sync, they are synced in such a way that minimizes their impedance to current flow. All right, so we need to find resonance. Let's do this. Number 4. Let's find resonance. Let's find the resonant frequency. And from I'll go through this the hard way. Let's find the resonant frequency, the resonant angular frequency, and that occurs when the inductive reactance is perfectly matched with the capacitive reactance. And I remember what inductive reactance is. It's omega D times L. And I remember what capacitive reactance is. C is in the cellar, so it's 1 over omega D times C. And you know what that means? If these two things are equal to each other, which means they perfectly cancel each other out, that's how I'm getting the resonant frequency situation. So I can write that as omega D equals 1 over the square root of LC. So I'm going, I guess I have to find my, well, actually, you know what? I do know this. I know that omega D equals 2 pi F. So once again, I'm just saying birth of a radian says omega equals 2 pi F. And I'm just using the subscripts here. Omega D, that driving frequency, is 2 pi times that driving frequency. Yeah, I guess I'm using uppercase D's. Yeah, okay. So number 6. Let's solve for LC. Right here, solve for C, I should say. Solve for C. That's what we're being asked to do. If I know everything else, let me do a little sanity check here before we go to the calculator. Do I know the value of 2 pi? Yes, I do. Do I know the value of my driving frequency? Yes, I do. My driving frequency for me is given right here. So I know everything on the right side. Do I know the value of my inductor? I do. So then solve for C. Let's all solve for C, get the right answer. Okay. All right. So I know what my capacitor value needs to be for resonance to occur. If when resonance occurs, so I'll just postscript this a bit here. So C equals 1.2275 and some change, 1.2275 e to the minus 4 farads. And then I'll say this, or at this capacitance, I have the following. At this capacitance, resonance occurs. And if resonance is occurring, that means the current, whatever current's flowing through this circuit is going to equal its max value, its maximum possible value, because the impedance is at a minimum. If I have this capacitance value, then the reactance of my capacitor is going to sync with the reactance of my inductor so that they basically offset each other as much as they can, or actually completely. All right. So what about B? Part B. Part B. We'll do maybe part B and C, then take a short break. But numbers, I guess I'll go over here. Number 7, part B is saying, okay, now that you know what to do to get that resistor to crank out as much heat as possible, what about the minimum? So C, what value do you have to set C to such that that power produced by the resistor, which is creating heat, is going to equal its minimum value? Okay, so this is what we're after. Number 8, I'm going to remember, well, I'll say this. Well, here I want to minimize. Here I want to minimize the current. I don't want to maximize. That was part A. I want to minimize. Here I want to minimize the current flow. So if I minimize the current, I'm going to minimize the heat that gets produced by the resistor. So here's my expression for current, number 9. Well, Ohm's law says V equals IR, but let's personalize it for AC. So in AC, I say EMF equals I times impedance. So this is, again, this is AC Ohm's law. All right, so let's keep going with number 10. Maybe I'll go over here. Number 10. So I equals the EMF all over the impedance. And I know what impedance is. Impedance is this thing again. Impedance is brought to you by the Pythagorean theorem in that phasor diagram, and is the aggregate resistance to current flow, XL minus XC squared. All right, so now that the question is, well, this is fixed. This is fixed. I can't mess with this. My numerator is fixed. Mine's 23.2 volts. But I can mess with the denominator. Well, I can't mess with R. That's fixed as well. All right. And in fact, I can't mess with this. The only thing I can mess with here is everything else is already set. I can, though, alter my capacitor to get what I want. So here's the question. What do I need to do in step 10? If you look at step 10, well, if Z equals Z max, you know what that means? I goes to I min. Okay, and that's what I want. So what do I have to do to that denominator to maximize it? So I'm going to look, I can't mess with anything. The only thing I can alter or examine is this. So number 12 says, if XC equals, C means in the cellar, omega D times C, I can say the following. If C equals 0, that means X sub C goes to infinity. If X sub C goes to infinity, Z goes to infinity. If Z goes to infinity, I goes to 0. Okay, and that's my minimum. You can't get less than 0. So let me just trace through that again. All right, so I'm saying here, if everyone is good with Ohm's law here, that's AC Ohm's law, I can't modify EMF or the resistor or the inductor, but I can mess with the capacitor. And I'm saying, well, if this is what the inductive capacitance is, the capacitor's version of resistance, then if C goes to 0, the capacitance, the capacitive reactance goes to infinity. If this number goes to infinity, so if this is going to infinity, then Z goes to infinity. And if this whole thing goes to infinity here, then anything over infinity is 0. So I equals 0. All right, so that's the answer. If you, and what does zero capacitance means? It means you take the capacitor out of the circuit, in essence. Or sorry, I should say you basically, it's a blank circuit. It's an opening, it's a gap. So it's an open circuit. So I'll just exit out. That's, so if you just surgically remove the capacitor from the circuit, there's basically no current flow. This is maybe one way to look at it. That's part B. All right, so let's do this. We've finished part B. We've finished part A and B. Time check, it's 9:18. See you at 9:28 a.m. for more quizzes. See you at 9:28 a.m. because it's not. All right, so yeah, break time. Okay, it is now 9:28 a.m. That's part A. Part B, yes. Part C, it says, C says, what are the maximum dissipation rate and the corresponding phase angle and power factor? All good stuff. Let me clear the decks. I think I can clear the decks. Can I? Yes. Except we'll see. I'm gonna store my capacitor die. So let me just wipe this out. Okay, we are on part C. What's the maximum? What is the maximum dissipation rate? Okay. Number one. Part C says, well, now that you know what you need to do to get the maximum, now you know what you need to do for the capacitor to get the maximum amount of energy dissipated by the resistance. We're going to actually find out what is that maximum rate. So what is P max? And again, P max occurs, let me write it like this. What is the maximum power dissipated by that resistor? And we said, well, that equals I squared R. Power is I squared R. But now we're saying, what is the maximum dissipation rate? Now we're actually going to have to use the RMS. So number 2, for AC, for alternating current, use RMS, root mean squared. Use RMS values for EMF. Use RMS values for the EMF, for power, for current. Okay. So remember, RMS stands for root mean squared, which is basically how you take the average in the world of AC. So we need to find this. We need to find RMS. P, the power dissipated by that resistor, RMS. That's what we have to find. And that equals, it still equals I squared R, but it's going to be I RMS squared R, I guess. What R? Yeah, R. So this is what we have to figure out. This is, let me just squeeze out all of the learning goodness from this. This is average current. Average current in the world of AC is referred to as RMS, or root mean squared current. So we are looking at the average current squared, and then this is the current going through the resistor, which produces the heat dissipation. Current through resistor, which creates heat. Okay, it's number 4 then. All right. Well, here's IRMS. So the power dissipated through that resistor, and we have to talk about RMS now, is IRMS, which is going to be I max over square root of 2. That's my RMS current times R. And just note, RMS equals I max divided by the square root of 2. You might say, hey, Chris, shouldn't it be just divided by 2? Not in the world of AC, not in the world of sine waves. And again, the math background is provided in your green sheets, but that lecture video is still my favorite way to say it. It just turns out we divide by the square root of 2 when you deal with AC, when you deal with a sine wave. If we dealt with a square wave, we do something else. If we dealt with a sawtooth wave, something else. Okay, so this is what we have now. We have the maximum power dissipated through that resistor is going to equal I max squared times R divided by 2. Aha, so there's the divide by 2. But we have to go through these steps. Equals, and I think, do we have this? Well, here's Ohm's law. Ohm's law is going to be the max EMF all over Z squared times R over 2. So the only substitution I made here is I said, all right, I max according to Ohm's law is just this. And let me just sidebar that. Ohm's law says that V equals IR, means in the world of AC, maximum EMF equals maximum current times impedance. Okay, so that's where this came from. So then I max equals maximum EMF over impedance. There it is. So now what? Number 6. We have maximum power. Word like this. This maximum power dissipation occurs at resonance. So if we have resonance means whatever the contribution from the inductive reactance, it's going to be perfectly offset by the contribution by the capacitive reactance or the capacitor, which means Z, and by the way, Z equals R squared plus XL minus XC squared is just going to equal R. Z equals R at resonance. So you know what that means. Number 7, this maximum power generation by the resistor, the RMS value of power, which dissipates in the form of heat, is just going to be, look at 5 and 6. So if I look at 5 and I look at 6, it's going to equal the maximum voltage squared over R. Over 2R, I should say. I almost forgot the 2. Okay, so let's plug that in. All right. Watts. We're done with A. We're done with B. We're done with C. And the big breakthrough here for part C is we applied RMS values, root mean squared values. Root mean squared is basically how you deal with the averages from a sine wave. Okay. Oh, there's more. Part D, phase angle. 7, 8. So number 8 says phi equals the dollar sign. Phi equals the dollar sign for part D. What's the phase angle? So this is just a great chance for me to once again draw the super important phasor diagram, which I will do here. All right, so I'm just going to run through this maybe perhaps a bit quicker than last time. This is my voltage drop across the resistor at some arbitrary moment in time. This is the voltage drop across my inductor, Eli the Iceman. This is my voltage drop across the capacitor, like that. And let me label this. This is my voltage drop across the capacitor, V subscript C. This is the voltage drop across the inductor, VL. This is the voltage drop across the resistor, VR. And once again, I'm just going to write down the world's most famous mnemonic, Eli the Iceman. World's most famous mnemonic, at least for RLC circuits, Eli the Iceman. Eli the Iceman tells us that, for an inductor, here's my inductor. When I'm looking at an inductor, voltage leads current, because right here, this is voltage, this is current, and this is you're seeing voltage lead current right here. Ready, set, go. This is always 90 degrees. And you might say, hey, Chris, you're drawing voltage leading voltage. And then I would respond by saying, you're right. Let me be more precise, because the circuit current is always synchronized with the resistor, because the resistor is just a dumb physical device. A resistor does not have any complex electromagnetic behavior like an inductor does or a capacitor does. So that's why this is current. So you're looking at Eli. This is Eli. And now you're going to look at Iceman. Iceman means the following. It means that when you look at a capacitor, this is the capacitor, C for capacitor. When you look at the capacitor, you know that current leads voltage. Here's current, I for current. Here's voltage, E for EMF. And yes, this is always 90 degrees, and this is trailing. Okay. All right, so what is the phase angle at resonance? This is what we do. So this is what you would do. I'm gonna copy and paste this blue vector. Maybe not quite like that. Copy. Wait a minute. I think I have. All right. Trying this again. Let me restart. I need to restart. So I'm going to take, this is how you work with phasor diagrams. Phasor diagrams are not unique to RLC circuits. There's phasor diagrams in a lot of different branches of engineering and science. So there's my blue vector. Okay. So I'm going to do my vector operations. It's always head to tail, head to tail. So there's my blue vector. And now I'm dealing with my blue vector, which is my inductance. And then here's my red vector, which is capacitance, the voltage drop across my capacitor. So I'll move that tail to head, tail to head. And at resonance, you get this perfect offsetting. You can see it right there. At resonance, the voltage drop across the capacitor perfectly matches the voltage drop. Let me say it again. At resonance, the voltage drop across the inductor perfectly matches the voltage drop across the capacitor. So here's my net vector. My net EMF, my EMF at this point in time is just connected. It's first tail to last head. This orange vector is the EMF voltage right there. And once again, I think I said this here. I said, here, I did say it. Phi, the phase angle is the angle between the EMF voltage and the current. So here's my EMF voltage right here. Here's my current vector. It's hidden. It's that black vector. It is this black vector right here. And you can see the phase angle is 0. Okay. So the answer to D is, and 0 is the phase angle at resonance. So you know you're in resonance when you have a 0 degree phase angle, because the inductor and the capacitor are perfectly offsetting each other, thus allowing the maximum or most efficient current or circuit. Part E is something brand new. Part E says, what's the power factor? In your lecture notes, here's power factor. So power factor right here. This is basically what you see on the screen. Is it's not, I wouldn't say it's new. It's just it's something I just ran through. So power factor, this power factor section is saying, hey, let us remember what Ohm's law is. Let us remember that we have to use RMS values when we deal with AC. And now we're going to do this. We're going to say, well, here's my phase diagram. There's the phase diagram that I just drew, except I'm just drawing it this way. Let's see. Here's VR is perpendicular, or VR. So everything's good. Okay. So anyway, I know what phi is. Phi equals to 0. So in my triangle right here, here's my triangle. Here's a triangle at this situation. Let me do this just so it's a little more insightful. What if my capacitor voltage, what if my capacitor didn't quite perfectly offset the inductance? What if I had something like this, not resonance? So what if that was my red vector? If that was my red vector, this would be my orange vector right here. My orange vector would look like this. If that's my orange vector right here, this is my phase angle, like that. Okay. So what we're going to do in terms of a rating system, so we're just going to agree to say, hey, how good is your circuit? How efficient is your circuit? We're just going to take the cosine of this angle right here, right like that. And you can see that if I just look at this triangle, what is the cosine of phi? Cosine is side adjacent, which would be the voltage drop across the resistor divided by the hypotenuse, which is the EMF. Okay, so we're going to always take the cosine of this angle, the phase angle, as our power factor. So in this particular case, we have this. Let me backspace that one. We have, how far can I go? There. This is what we have here. At resonance, this is our phasor diagram. At resonance, phi equals 0. There is no angular separation between the EMF and the circuit current. And that means in our rating system, cosine of phi equals cosine of 0 equals 1. And ta-da, 1 is the greatest possible power factor. So, you know, when you evaluate circuits, and you can do this in computer applications and electronics, you can do it for the power grid. If you need to find out how efficient things are, go ahead and figure out what that power factor is. 1 is the greatest possible power factor. And then what often happens in terms of our power grid, we need to add capacitance or add inductance to make things closer to 1. So that's why when you're driving around the neighborhood and you see these power substations, let me get a quick picture of this. Power substation inductors. I think they're called capacitors. Okay. So there's a pretty good picture. Let me open this in a different open image in new tab. Okay. So when you see this type of alien looking equipment, you're looking at transformers, capacitors, and inductors and other stuff, but very predominantly transformers, capacitors, and inductors. And again, the inductors and capacitors are sort of adjusted or working in whatever way they need to work to maximize efficiency, because you get these unwanted effects and you have to overcome these unwanted effects by messing around with the capacitors or the inductors. Okay, so that's power factor. And at this point, I don't think there's anything brand new that you're going to get hit with in chapter 31. RMS, we've now covered RMS, what it means, how to deal with it. We've covered power factor. We've covered power. Let's finish this problem. Power factor. All right, so we're done with E. What about F? F says the minimum dissipation rate. We've already answered that. So, but let's say a few words. Let's just say a few words about that. Part E says, okay, on the other extreme, what is the minimum dissipation rate? Power, what are F, the minimum dissipation rates? So here comes F. Minimum dissipation rate. So P across the resistor, we have to talk in terms of RMS. At some point, we just stop writing RMS. We know that we're going to use RMS, but now we're talking about the minimum. What's that minimum value? Well, it's going to be I RMS squared times R, not Z, but R. If I was going to write down I squared Z because Z is the AC version of impedance, but we're only talking about the power dissipated as it goes through that resistor. So that's why it's I squared R, I RMS squared R. Right. So number one, number two, well, if C equals 0, basically an open circuit, if C equals 0, an open circuit, I RMS equals 0 because Z once again goes to infinity. So just to repeat that. So there is no, if no current flows, no heat is dissipated by the resistor. That is F. We've done A, B, C, D, E, F. G, phase angle. This is different. All right, so for the umpteenth time, let's draw a phasor diagram. At some arbitrary point in time, here's my voltage drop across the resistor. Here's my voltage drop across the inductor, something like this, Eli, thanks to Eli. Here's the voltage drop across the capacitor. Minimum dissipation rate. All right, so if my capacitance is equal to 0, my inductance is approaching infinity. So here's my, let me say it again. If my capacitance is 0, my capacitive reactance is approaching infinity. So ready? Let's just draw this off to infinity. Okay. Maybe even longer. So I'm just going to make it super duper long because it's supposed to be, I got to make sure it's 90 degrees. Iceman means it's trailing by 90 degrees. Let me actually zoom out a bit. So here, I'll draw this going off to infinity. And even though that's going off to infinity, let us not forget that this is Eli, so that's plus 90. Let's not forget that this is Iceman, so this is negative 90. All right, so if the capacitance equals 0, the capacitive reactance, which is this is the voltage drop across my capacitor, and it's associated with the capacitive reactance. That's infinitely long. I'm going to take a copy and paste of this, copy, paste, and do my vector operation as usual. Move this in position. Tail to head. Okay. Now, to be honest, this orange capacitive reactance is being offset by this inductive reactance. I'm going to do a copy and paste of that, but it's still infinity. Because what happens if you take an infinitely long vector, like what I'm trying to show here with this orange vector? What happens if you take an infinitely long vector and offset it by this little teeny tiny contribution by the inductor? It's still infinitely long. Okay, so here's the EMF voltage at this particular point in time. It looks like this, like that. Okay. So this is my EMF voltage. This is my circuit current right here. Let's not forget that current's the same everywhere. And let's not forget that this green vector was my voltage drop across the resistor. So now play this out. What if this orange line truly goes off to infinity? If this orange line is going off to infinity, like kind of I'm doing here, as this keeps getting longer and longer and goes off to infinity, this red vector, which is, I'm having a hard time, there it is. This red vector basically starts to do that. If this orange line went to infinity, my red vector would keep going like that. It would follow it off to infinity, and I would start to approach this value right here. So what is this phase angle right here? Is phi equals negative 90 degrees, because phi is the angle formed by this vector here and the current vector here. And as that orange vector goes off to infinity, it starts to approach negative 90 degrees. All right, so is that? Oh, what's the power factor? So this is the worst case possible. We just looked at the best case possible. The power factor, which is our rating system, just take the cosine of that phase angle. The cosine, so here, power factor. What's the power factor? Cosine of phi. That's the power factor equals 0. 0 is the worst possible case. 0 means there's no current flowing. 1 is the best possible case. It means you have the most efficient circuit you can get. And we're done. We're done with this problem. So now we have to do a Fallstad on this, I think. Let's do a Fallstad for power dissipated by the resistor. So let's go off to Fallstad and we'll use my numbers. Let me clear this. And then you can submit the link in the chat box, and that's how you collect free points. All right, so off to Fallstad. Let us go off to Fallstad. Let us do circuits, blank circuit. So brand new sheet of paper. Let's create, it's an RLC circuit, so I guess maybe I didn't need to trash it, but it doesn't take long. Right click, inputs and sources, AC voltage source to terminal. Right click, add resistor. Right click, passive component, add capacitor. Right click again, passive component, add inductor. Okay. My numbers, let's all use my numbers. For me, the resistor is 4.33 ohms. Double click on the resistor. 4.33 ohms. There. Because again, I'm just using my numbers. 4.33 ohms. My inductor is 51.5 millihenry. Double click on the inductor. 51.5 millihenry. So just 51.5 M. My capacitor has a value of, I figured that out. So I have to type that in. I think I still have that in my calculator. Hopefully I do. All right. So my capacitor has, what is that? 1, 2, 3, 4, 5, 6. Okay. So the capacitor, double click on your capacitor. Okay. And let's enter a value of let's just do 1.22751166 E minus 4. Again, 1.22751166, I should say. 626 E4. Yeah, I got that right. And let me just type that in again. All right. So 1.22751166 E minus 4, and then say okay. I guess I meant to say, try that again. 1.22751166. Well, I don't think it likes E minus 4. So you know what? What would that be? It doesn't like E minus 4. So that would be, let's instead type in 122.7511626 U. Okay, it doesn't like E. Okay, there. All right, and let's double check that. Okay. So it didn't like the U, so that is the same. I think these are equivalent. Okay. All right. So let's talk about the EMF. The EMF, my EMF hits a peak voltage of 23.2. 23.2. Max voltage 23.2. Now we have to do a little bit of work again. 23.2 max voltage. We have to set this to resonance because we're going to figure out what is the maximum power dissipation. The maximum power dissipation occurs at resonance, which means we have to go back to here, to our workspace. We have to remind ourselves what resonance is. Here's resonance. Omega equals the square root of LC, and that equals 2 pi F, because omega equals 2 pi F. Okay, so that means, you know what that means? That means F equals 1 over 2 pi square root of LC. And with my numbers, let's figure that out. What is 1 divided by 0.0515 divided by alpha A square root divided by 2 divided by pi. All right, I'm getting a frequency of 63.3 hertz. Actually, you know what we can do? Let's do this and that's fine. And let me double check that. I need to double check my numbers. 1 divided by L, 0.0515 divided by C, which is sitting there in alpha A, square root divided by 2 divided by pi. All right, I think it's 63.3. As long as I have my value. Okay, 60. All right, so resonance occurs at 63.3 hertz. Oh, darn, they already told us that. Oops, sorry, but good learning experience. They actually already gave us that 63.3. So back to Falstad. All right, set your frequency to 63.3, which was in fact given. There it is. So now you're looking at a resonating circuit. All right. So using math and physics, we said the maximum power dissipated in the form of heat through the resistor is 62.12 watts. So let's do this. Right click on your resistor in Falstad. Right click on the resistor in Falstad. And let me just make sure. This is what math and physics. Math and physics says 62 watts of heat gets cranked out. All right, so right click on the resistor and choose view in new scope. Got it. And then right click on this scope that just got created, properties, and we want to show power consumed. Okay. Show power consumed. Wait a minute. Not that. Hang on 1 second. RMS value. Power consumed. Okay. That's so the only box we're checking in the properties is show power consumed. Everything else is blank. All right, so say okay. And then there's always an adjustment period that has to happen. There's always sort of like a getting into groove period. There's a period of adjustment that happens. So let's just crank up the simulation speed. So let the simulation speed run to its maximum value so that we blow through the adjustment period and we hit a steady state value, and then you can just stop it. So according to Falstad, the average power produced when current flows through my resistor is 62.157. 62.157 compared to 62.152. And that's just because we haven't cranked up the accuracy, but that's a match. Fall stat is basically saying the same thing that math and physics predicted for us. So now you can go ahead, click File, Export as Link, create short URL, copy to clipboard, and go ahead and dump it into the chat box. And that will be your quiz credit for this particular circuit. Okay. Let's move on. You guys can do that as I set up the next one, the last quiz. Chapter 31, quiz 10. Let's just take a look at Luke since it's just staring at me. Max out. Good, Luke. Luke caught. That's not correct. So Luke, you need to revisit. That is an incorrect result. Let's look at Mo's. That's incorrect. So if we're 0 for 2 so far, unless I'm looking at the wrong ones. Am I looking at the wrong ones? Let me see. No, I'm not. So Mo, that is not correct. Luke, that is not correct. Anyone else? Maybe I want to. Here's Jordan. Jordan, that is correct. Dan, that is not correct. So some of you has some more work to do. No, I take that back, Dan. You are good to go. So Dan, you are good to go. Jordan, just double checking here. Jordan's good to go. Mo, maybe I made a mistake. Mo, not yet. You are still working on it. Luke, Morgan, you are good to go, Luke. So I think I misspoke before. You are good to go.
Sorry, what my Zoom audio?
What's that? I'm sorry.
My Zoom audio cuts out for reasons that I don't know sometimes. So I did.
So you what? Well, maybe you cut out again, but yeah, Luke, you're good. Your circuit looks good. Julia, your circuit looks good. Okay, so just maybe certainly speak up. But I mean, here you can self-correct, you guys. You don't need me to tell you. All you need to do is you need to look at what I'm like. When I click on the link from Julia, let me just redo that. Here's the link from Julia. When I click on it, this is what pops up on my screen. And the only thing I'm going to be looking for is to make sure when I run this at maximum simulation speed that I'm looking at that 62 point. Here, I'll stop it. I'm looking at that 62.157 number. 62.157 watts is the average power dissipated through that resistor at resonance. So let me just take a look at.
Can you go back to your data real quick? Because my computer crashed when I was building the circuit, and I had to rejoin everything. So and I lost like everything.
Matt, you're going to have to retake this class next semester. Sign up now. Yeah, I will. Stephen, no, you're not there yet either. So again, you guys, you don't need me to check your work. Check your own work. If you're not getting 62 point something, whatever that number was, you're still working on it. So Matt, you needed to see these numbers, or you need to see my false stat.
Your false stat. Also, how did you get the graph to come up? Because between the time of my computer crashing and me getting back on, I missed that entire instructional piece.
Okay. I think this was me. All right. So, all right, here's the circuit. So let's just go through this quickly again. There's your EMF RCL. Your resistor value is 4.33. Your capacitor value is 122.7511626 U. Where did that number came from? Where did that number come from? It came from the problem where it said, hey, what does the capacitance need to be for resonance? So for my numbers, it was 122.751 626 U, which means microfarads. Then you can say, okay. My inductor was 51.5 M, which stands for 51.5 millihenry, which means 0.0515 Henry. Last but not least, the EMF. This EMF is producing a peak voltage of 23.2 volts. And they gave us the frequency, even though I recalculated it needlessly, they gave us a frequency of 63.3 hertz. So those are all the settings for the EMF, the R, the C, the L. Then what you do is you hover your mouse above the resistor or on the resistor, hover your mouse over the resistor, right click, and then say view in new scope. View in, if your scope, it actually doesn't matter what the size of your scope is, but you can adjust the scope size. So if I wanted to, I'm trying to do it. Why is it? Oh, that. Wait. All right. This is fine. You can have just a whatever. You can resize this scope. It doesn't matter. Right click anywhere on the scope area. Say properties, and the only blue check. It's like Twitter. The only blue check mark is going to be show average, was it? I think so. Show current. Yeah, that's it, I guess. These are the only two. Show power consumed, show average. Okay. Those are the two blue check marks. And then you hit run, and just to maximize, just to blow through the adjustment period, you crank your simulation speed all the way to the right, and you should kind of settle down on about that average. So right here, this top left average, right where I'm hovering my mouse, if I stop my simulation and I'm hovering top left of this graph, right, top left portion of this graph, it says 62.153 watts are being dissipated in the form of heat via that resistor, which again, if we went to look at the math and physics, that agrees with what we got using math and physics. Okay. All right. Let's do chapter 31, quiz 10.
You're getting a wattage output. I'm getting a voltage output.
That's here. So let's go to, we need voltages and power. So
Yeah,
you need
no, I know.
right click on your, let me just back that up. All right. So if you hover your mouse above the resistor, right click on the resistor, view in new
Okay.
scope.
I had both voltage and power consumed, but it wasn't
That's
showing
fine.
power consumed.
So yeah, if you don't, let me know if you still have questions, but keep hammering away on it until you're good to go.
What is this supposed to be?
What'd you get?
It's still settling, but it's 62.13 to 62.16, and it's just going
Yeah. Yeah. And again, if you crank your simulation speed to max, you're gonna blow through that getting settled period. So yeah, like when I do it, I need to change it. I need to right click on my properties. I don't want to show voltage. I want to show power consumed. Okay. And then that's not right. I need to properties, show I don't want peak power. I want average power. And average means in this context means RMS there. Yeah. So 62.15 something. All right. So that's, let me get the last or the next quiz ready. Chapter 31, quiz 10. Chapter 31, quiz 10. It's now 10:17. All right. Chapter 31. Chapter 31, quiz 10 is now open. It should be problem 59 and look like this. Okay. This is our last chapter 31 quiz. If time allows, we'll do a chapter 29 quiz. We'll see. Because we need to take a break pretty soon. In fact, let's do this. And then we'll take a break and then we'll blow through to the end doing 2 problems. So see you at 10:28 a.m. And then when we come back from the break, we'll just work for 1 straight hour to finish everything. Chapter 31, quiz 10. Let me double check. Yep. Okay. Chapter 31, quiz 10 should be viewable to you and should look like this. Okay. This is, in some ways, this is like the ultimate problem. This kind of ties together, maybe not everything, but a lot of stuff. We have an RLC circuit. We know what the generator is doing. We know the frequency. What's the RMS current? Number one says I RMS is the $sign. That's for part A. This is part A. So they're giving us a lot of information. Here's Ohm's law. Here's Ohm's law. Well, if V equals IR, then that means I equals V over R, but personalized for AC, this actually becomes I RMS. We want the RMS current. I RMS equals EMF RMS. So we're just RMSizing everything over Z. This is the AC version of Ohm's law. And we're using RMS values, which is to be honest, that is sort of like the default approach. We're not interested in max values. We're interested, if we were interested in max values, that's fine. We've had problems where we said I max. The amplitude, current amplitude is the EMF amplitude over Z. That's totally legitimate. But we're now looking at the average values, which in the world of sine waves is referred to as root mean squared. Number three says, all right, the average current flowing through this circuit, what is the RMS current? Is the EMF, which is 68.9 volts, 68.9. That's the RMS. This is the RMS voltage. So needed to make sure about that. All over the impedance. Here's the impedance, R squared plus the inductive reactance minus the capacitive reactance squared, Pythagorean theorem. So let's run with these numbers. Equals 68.9 volts divided by, I'll do it like this. R squared is 19.9 ohms squared plus XL. Here's XL. XL is omega D times L minus XC. Here's the capacitive reactance, 1 over omega D times C, quantity squared. I'm going to do this. I'm just going to use my calculator. So omega D, my driving velocity, the rate at which my generator is spinning, because remember, if you spin copper, a coil of wire in the vicinity exposed to a magnetic field, you get all this stuff. But this is 2 pi f, which is given as 2 pi. The driving frequency for me is 708 hertz. So let's get a number on that. And then let's just store that in calculator memory location A. All right. 2 times pi times the frequency. Okay. So now what I can do is number 5. Here's my average current, not my peak current, but my average current. It's going to be 68.9 volts all over 19.9 ohms squared plus calculator memory location A times my inductor value. For me, my inductor value was 34 millihenry or 0.034 Henry minus 1 over calculator memory location A times my capacitance, and my capacitance was 5.25 microfarad. 5.25 e to the minus 6 farads. This gets squared, and then this is square rooted. R squared plus, that's right, I think. All right, so let's find out what our average current is. Double checking, 34 millihenry. All right. Okay. Quite the calculator workout. So I know my average current. Okay. Part B. What's the voltage drop across the resistor? So let me just continue here in a different color. This is what we're after for part B. What's that voltage drop? Part B. Excuse me. So part B, what's the voltage drop across the resistor, not the inductor? The resistor. That's our dollar sign for part B. So part B, let's do Ohm's law. Ohm's. What is the RMS voltage across a resistor? So again, we're not looking for peaks, we're looking for averages. Ohm's law here says V equals IR let's customize it. That means the voltage across the resistor, RMS, equals the RMS current, which I just figured out in part A, times the resistor value, R. So we're done with part B. Let's just take that current and multiply by R and get the answer. That's the answer to part B, 12.437. Volts. Done with A, done with B. Now, same exact thing for the voltage drop across the capacitor. Part C is saying, what is this voltage drop across the capacitor? That's the dollar sign. So let's just, I'm going to keep going here. Part C, I guess that same numbering, says Ohm's law. Ready? Here's Ohm's law. V equals IR. Here's Ohm's law. Oh, here's Ohm's law for the capacitor. It's V, the voltage drop across the capacitor, RMS, we're talking about RMS values, average values, not peak values, equals IRMS times the capacitor version of resistance, which is capacitive reactance, X subscript C. So then you just need to take your RMS current that you calculated in part A, which is sitting there. Hopefully, I put mine in calculator memory location. I put it back in calculator memory location A. All right, times the capacitive reactance. And here's the capacitive reactance. 1 over, 1 over omega, and omega is Q times pi times the frequency, 708. This is omega, because for the 24th time, omega equals 2 pi f times C. And for me, C is 5.25 e to the minus 6 farads. There. Okay. $26 and some change. 26.76 volts. This is the answer to part C. This was the answer to part B. So we're good on part B. 12 volt drop across the resistor. 26, whatever your number is, some voltage drop across the capacitor. D says, what about the inductor? D says there's a voltage drop associated with this inductor. I'm going to clear some clutter here. Okay. What is my voltage drop across the inductor? Part D. Inductor voltage drop is the dollar sign. Here's Ohm's law. V equals IR. But here, for an inductor in AC, we say the voltage drop across the inductor, RMS, the average value, not the peak value, equals the RMS current, which we figured out in part A, times XL, the inductive reactance, the inductor's version of resistance. So we have IRMS, that was the answer to part A, which I have stuffed away in my calculator somewhere, times XL, here's XL, omega D times L. All right, this is the inductive reactance, XL, with numbers equals IRMS, I'm just going to say that's just sitting in my calculator, times, and I should have stored this as well, but I didn't, 2 pi times 708, that's my angular frequency of my generator, times the inductance value, which is 34 millihenry, which is 0.034 Henry. Okay. $94. That's the answer to part D. Okay. So now this is where things got weird before, and they're weird again. So this sounds an alarm. Alarm. How can this be? How can VL be greater than the EMF? You should look at this number, 94.529. For me, 94.9529 is greater than my EMF voltage. My EMF voltage is 68.9. So if my energy source is providing 68.9 volts, how the heck can I get 94.529 volts across my inductor? And the answer is VL is getting offset by VC. That's why. So at any moment in time, you can have a voltage drop across the inductor that's greater than the EMF. But you have this offsetting effect, means that you're obeying the laws of conservation of energy. All right, so that's D. E says, what's C and L together? The voltage. So you know what you need to do for part E right here. Part E, and they're doing this for a reason. This isn't busy work. Part E. So we've silenced the alarm. It's not really an alarm. Part E is saying, just take those two voltage drops. This is part E. Part E is saying, what's the voltage drop across my capacitor plus my voltage drop across my inductor? And I got this. My voltage drop across the capacitor is in part C. So for me, it's going to be that 26.76 number. It's going to bring it back from my calculator, plus the voltage drop across my inductor, which is 94. Oh, but wait a minute. Do I add them? These are offsetting. So I actually have to say this. I'm going to do this. I'm going to actually I'm going to say, wait, whoa, Nelly. Whoa, Nelly. Wait, because I forgot that 1, 2, VC and VL offset. They always offset each other at all times. How do I know that? Because of the phasor diagram so let us enjoy yet another phasor diagram. Here's my resistance. This is my voltage across the resistor. This is my voltage across the inductor. Eli means leading by 90 degrees. Here's my voltage across my capacitor. Ice means trailing by 90 degrees. This is my voltage drop across my capacitor, my voltage drop across my inductor, my voltage drop across my resistor. And this is where they offset. So this is what I'm saying. Wait a minute. Whatever this value, whatever these values are, they offset each other. So the way I should calculate part E, part E is saying, what's those voltage drops together? I'm going to do it like this. I'm going to say number 3. I'm just going to say, what is VL minus VC equals for me? VL was the answer to part D, which is my number. This is my voltage drop across my inductor, 94.529 volts, minus the voltage drop across my capacitor, which is part C for me, that 26.76 number. That is the difference. When I sum those together, this is what I'm going to get. 94.529 minus 26.76, or 67.76 and some change. 67.768 and some change volts. Okay. And I'm definitely keeping all of this stuff in my calculator memory, because apparently everything's getting reused. This is the answer to part E. This is how my inductor and capacitor are working together from a voltage point of view. Part F says, let's add them all together. Okay, to do that, back to the phasor diagram, which is already created, so I don't need to recreate. So here's what we're going to do. We have to use Pythagorean theorem. All right, what if I just have maybe that? I'm going to copy and paste this blue vector. Copy and paste. Okay. I'm going to offset it by that light blue vector. There you go, like that. And here's the answer. This orange vector. Ready, set, go. Okay. That's my orange vector. This is the combination of the voltage drops across my resistor, capacitor, and inductor. This is, in fact, my EMF voltage at the time. Let's label here. So here's the triangle. Here's the triangle I'm working with. This is my hypotenuse. So here's my hypotenuse. Got it. Here's the other leg of my triangle right here. This is VL minus VC. This triangle leg is VR. Okay, so to get the answer to part F, when we blend all of this stuff together, it is Pythagorean theorem, number 4, part F. All right, I need to combine, but I have to combine them together vectorially. So here's what we go. Here's what we have. I'm going to take VR squared plus VL minus VC squared and take the square root of all of that. And you know what that is? This is going to be the net effect, net voltage across RC and L. So with numbers, number 5, I'll just say voltage net equals my voltage drop across the resistor, which I have that. That's from part B, 12.43. So my part B was 12.437 and some change squared plus VL minus VC, which is this number right here. So I already have that. This is VL minus VC. This is the net effect of my voltage drop across the inductor and capacitor. So that is already sitting there in my answer to part E, which was 67.768 and some change squared. And then we take the square root of it. And up here, I should have wrote over here, I should have written down, I'm not squaring this. I'm taking, this is Pythagorean theorem, because this is just keying on this triangle. This is the triangle I'm using right here. That's 90 degrees. Okay, so let's get the net voltage. Okay. 68.9. And some change. 68.9. So this is a huge aha. Is it? Yes, it is. This is gigantically meaningful. So I'm going to have to use a special purple vector saying aha. Here's the moral of the story. The voltage across R, L, and C at any moment equals the source. So this is Kirchhoff's loop rule. If we go around this circuit and we say, hey, well, okay, we've got, for my numbers said I'm investing, my voltage source was 68.9. 68.9 in, then I have a drop across the resistor, then I have a drop across the VL plus VC. And that should equal 0. But you have to do this it's the loop rule. This is for sure the loop rule, but you can see all of the care we had to take in setting all this up. So it's more complicated than just basic math. But that is a huge aha. And a lot of work went into getting to this point. So that's why this problem is especially useful, because it's tying together a bunch of stuff. But we're not done, but we're very close to being done. The last part goes quickly. Okay, part FG. What is the average rate of energy dissipated by the resistor? So that will go. We can do this. So G, part G is saying the average rate of energy. So the power dissipated through the resistor, and as soon as they use the word average, that's RMS, equals I squared R equals I RMS I squared R. And we have that. This is the answer to part A. So for me, the answer was 0.624 and some change, 62499. Square that times the resistor, I squared R. For me, R is 19.9. I squared times 19.9. This is how much heat gets generated. This is the number of joules per second, 7.773 joules per second, or 7.773 watts. That's how much heat's getting generated by that resistor. And look at the answer to H and I. H says, do that same calculation. What is the average power dissipated across the resistor? I'm sorry, across the capacitor. So power across the capacitor, RMS, you know what, that equals 0. And part I, what is the average power dissipated across the inductor? That equals 0 as well. And that's because of the following. Capacitors and inductors store energy. They don't dissipate it. Capacitors and inductors store energy. We like them. We like them because they're energy storage devices on top of other applications. Capacitors and inductors store energy. They don't dissipate it. They don't dissipate energy. They don't dissipate. Whereas a resistor does. They don't dissipate energy. So it's good to have that little reminder. Capacitors and inductors are electromagnetic devices, whereas a resistor is just sort of like it's basically like sandpaper. It's like an asphalt surface that you're scraping along. That's it.